Okay, we're going to talk about lesson 2.1 having to do with relations and functions. So go fairly quickly. Just a reminder, you can look in the book as well, lesson 2.1. These terms are in lesson 2.1 and they have some additional examples in there. Same thing when we get to linear functions, which will be 2.2. Some of these terms are going to be review from Algebra 1. First one, a relation. A relation is just a set of ordered pairs. Every time we have a list of ordered pairs or an equation that can be written and you can make a list of the xy coordinates, all of those are going to be relations, but it can be as simple as a relation being, put it in set 1, 2, 2, 3, 3, 8. Thought I was going to say 4, didn't you? This is a relation. It's a set of ordered pairs. There's 3 ordered pairs listed. The domain is the set of all x values, which is also known as the input values or the independent variables when we get into equations. In my example up here, my domain would be the set 1, 2, and 3. It's just going to be, in this case, it's just a list of it. Sometimes we'll do it in interval notation as we continue. The range, set of all y values, output values, or dependent variables. My range is going to be 2, 3, and 8 for the example that I have of my very small relation. Function, set of ordered pairs in which each member of the domain is paired with exactly one element of the range. Oftentimes we look at these as a mapping, and we look at I have 1, 2, and 3, and I have 2, 3, and 8. And as long as when we draw a line from the x's to the y's, each x only has one arrow coming out of it. In order to be a function, you can't have the same x having 2 different y's as a partner. I like to think of it as, y equals x plus 1. This is the input values or the domains. You can't put the same value in for x and get 2 different answers for y. Same holds true for y equals x squared. I can't put the same value in for x, square it, and get 2 different answers for y. Now in this case, I can get the same. I put 2 in there, square it, and get 4. And I can put negative 2 in there and get 4. But again, we're only worried about the domain values or the input values when we're concerned with whether or not it's a function. 2 different kinds of functions. 1-to-1, each element of the domain pairs to exactly one element of the range. This is going to be, linear functions are all 1-to-1, where again, this is a function because there's one value coming out, one value coming out, one value coming out. Onto function, each element of the range corresponds to an element of the domain. So now every single range is used. That's a good way to determine what's the difference. How do I know if it's going to be onto? All range values are used, and that makes it onto. If you look over here, C was not used, therefore it's not onto. And then none of the domain values go to the same range value. Well, how come this one right here isn't 1-to-1? Because 3 and 4 both go to C. That's not 1-to-1. That's not one domain with one range, one domain with one range. Here's 1, two different domains with the same ranges. That's what makes it one-to-one. So you're going to have one line coming out of each to make it a function. Both of these are functions. All the ranges are used over here. That's what makes it onto. There's one left alone. That's what does not make it onto. Here's an example of both onto and one-to-one. All the ranges are used, and therefore it's onto, and all of these just have one partner, and that's what makes it one-to-one. Discrete versus continuous. Discrete is these ones over here are discrete. If you're going to graph it and your pencil comes off the paper, that means you're graphing points, dot, dot, dot. Pencil comes off the paper, it's going to be discrete. So the discrete is going to be your plotting points is essentially what it comes down to. Continuous, you're drawing some sort of continuous line. That's what makes the continuous. Pretty self-explanatory there. One more thing. Discrete is often called countable. I can count them. Countable. Countable. This isn't countable because all of the individual values in between are decimals. We can't tell exactly where they are, so they are continuous. Vertical line test is for when we graph. So we're going to be looking at functions as a table or a list of ordered pairs, like we saw with my very crude example of a relation. We're going to look at them with equations, and then of course we're going to graph those tables, or we're going to look at a graph, or we're going to graph the equations. And the best way to tell on a graph and whether or not the equation or the list of ordered pairs is a function is by using the vertical line test. And if no vertical line intersects a graph in more than one point, the graph represents the function. So I like to move my pencil from left to right. If we move from left to right and we draw vertical lines in, so I've got from left to right, I'm moving verticals, verticals, verticals. And if I'm only hitting in one spot, well, that's not vertical. Whoops. If I only hit the graph in one spot, I will always be, I will be a function. And if you think about it, if you look here at this one, so I move it from left to right. As soon as it fails, it fails. So I mean, right here it fails. As soon as you hit more than one point, because if you look at these two right here, I've got 2 points on that vertical line. I have the point. It looks like, what is that? 1, 1 on top. Let's call it 1, 1 just for fun. And the other one looks like 1, -2. So if you go back to the definition of a function, each individual function has to be paired with one and only one output or y value. And so if I list 1 and did a mapping here, I'd have 1 and -2. And I am not allowed to have 2 arrows coming out of the same x value. You can't have a function if you have one going to 2 different values right here. So the vertical line test, very easy visual way to tell whether or not your graph is a function. So if you think about some simple graphs that we've worked with in the past, you have a, let's say you have a linear function. Boom, run a vertical line through this, vertical, 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 vertical. I hit it in one spot. It's a function. It works. We've got, this is a parabola. All parabolas will be functions. We're good to go. We run a vertical line. If you think about the absolute value graph, it's a V. Absolute value is a V. So we have vertical lines. These are all functions because I'm only touching it in one spot as I move it from left to right. Cubic is a function. Cubic works. Looks something like that. That's ugly, but it still works itself out. Vertical line touches it in one spot as we go across. Well, I guess I have a terrible drawing here, so that doesn't help. But if you graphed x cubed nicely, and I get the nice, like that guy. I'm still bad up here. Anyway, you get the picture. Vertical line test. They have a couple more examples in the book similar to this. And if you can run, so a circle is not a function because as soon as you run a vertical line and hit in two spots, it fails. Vertical line test. Pretty nice, easy way to look at a graph. The last thing, the last thing for 2-1, this is the end of 2-1, function notation, the symbol f of x. So when we're often talking about f of x, and it's read with the term f of x. This is going to replace y. So y equals mx plus b, or y equals 2x plus 7. Instead, we're going to have f of x equals 2x plus 7, function notation. It's just going to be exactly the same. The reason I like function notation better is it shows you an ordered pair. For example, instead of just plugging in a value for y, if I want to know what the ordered pair that goes with the number 1 is, all we're going to do is it's telling you what to replace. So I'm replacing the x with a 1. 2 times 1 plus 7, I get 9er. So I have f of 1 equals 9. I have the ordered pair of the input or domain value of 1, output range value of 9. I can clearly see it's 1, 9. So we go over here, find m of 3. So this is m of x is 4x plus 2. All I'm going to do is 4 times 3 minus 2. Let's make sure that we're using some equal signs as well. 12 minus 2, I get 10. M of 3 is 10. And then we've got k of negative 2. Now, you got to be careful. Make sure that you are putting in negative 2 squared plus 3. You're squaring the entire value of h. In this case, h is being replaced with negative 2. Please make sure that you know how to do that in your calculator properly. I get 4 plus 3. Negative 2 squared is positive 4, and I get 7. K of negative 2 is 7. Now, you will have some where you have to do some more operations, such as, what if we had to do 5 times m of 3? This means we're going to figure out what m of 3 is, which we just did, was 10. Then I'm going to take 5 times that answer and get 50. So all of our order of operations will hold true. Or what if you had m of 3 times k of negative 2? Well, first we figure out what m of 3 is. In this example, it's 10. And then we figure out what k of negative 2 is. It's 7. And my answer is 7. So I think this is kind of a review, this lesson 2-1 from Algebra 1. You've seen it before, but you really can't talk about functions enough when it comes down to, can you understand that it's the x's that really dominate everything? They're the domain. They're the ones that can't double up and repeat. Now, 2-2 is linear functions. Linear functions, you're most comfortable with y equals mx plus b. That's slope-intercept form. We will be dealing with that. But you can always tell if a function can be written in ax plus by equals c form. That's called standard form. So when they ask you to write something in standard form, first of all, a is greater than 0. A must be positive. Second of all, a and b can't both be 0. If they're both 0, I have 0 equals c. I have no variable. You have no equation. Also, they are all integers, no fractions, no decimals. And lastly, they're reduced, so to speak. What do you mean by greatest? This is greatest common factor is 1. So if I had 2x plus 3y, 2x plus 4y equals 8. This is not in standard form. They're all integers, and they're these two are not 0 and a is positive, but I can divide them all by 2. X plus 2y equals 4. That's standard form. Oftentimes you need to try to write them in standard form, so I look at these first two and I think I currently have things in the denominator, so I need to multiply by y, and I get both sides, and I get x equals 5y. Secondly, I need to subtract 5y from both sides. And can I do x minus 5y? Nope. X minus 5y equals 0. The value of a is 1. The value of b is negative 5. The value of c is 0. We are good. A is positive. They're all integers. The greatest common factor is 1. And it's written in standard form. The next one, times x times x. 3 equals xy. Is this in standard form? Is it linear? No. There's no plus or minus in between the x and the y. We can't do it. And the last one, it has a squared term. X squared minus 2y equals 0. Linear do not have squares. It must be or cubes or any power other than to the power of 1. X-intercepts and y-intercepts, they're going to ask you to graph some of these. An x-intercept, where the graph crosses the x-axis, it's going to be an ordered pair of something comma 0. So what we're going to do is we're going to figure out, we're going to put a y value of 0 in. So calculating the x-intercept, I'm going to do 4x minus 3 times 0 equals 12. 4x equals 12. X equals 3. Boom. I know that my x-intercept is 3, 0. We'll scroll over to 1, 2, 3, 0. Plot it. Y-intercept. It's going to be when the x value is 0. Think about the y-intercept. We're not going left or right, which means I'm dictating that it's 4 times 0 minus 3y equals 12. 3 minus 3y equals 12. And then y equals negative 4. Watch your sign. I get 0, negative 4 for the y. So I get 0, 1, 2, 3, 4. I go down there, grab your trusty straight edge, do some graphing. Let's see how I did. That's not bad. Put some dots at the end, or some arrows at the end, and we are set. So when they ask you to graph using the intercepts, x-intercept, that's going to be on the x-axis, which means I'm not going up and down. That means you're going to have a y value of 0. And then y-intercept means I'm not going left and right. You're going to have an x value of 0. Makes it very easy to solve the equations when you do it like that. So that's a pretty quick version of 2.1 and 2.2, relations and functions. Again, I encourage you to take a look at the beginning of the chapter, but you should be able to get going on your homework for both of these sections right